As we will see, throughout this course, we are frequently referring to power, output power, and power gain of amplifiers and other circuit blocks. The question is, why power? To answer this question, one should recognize that at low frequencies, power gain is abundant. Therefore, at low frequencies, the best possible way of evaluating a circuit performance is through voltage or current gain. In a striking contrast, the RF circuit design is frequently preoccupied with power gain. And the primary reason for this is that when we evaluate the performance of a wireless system, for example, a wireless receiver, we normally evaluate the performance of these systems against impairments such as noise and distortion. For example, the sensitivity of the wireless receiver is defined to evaluate the minimum detectable signal for a receiver. And this minimum detectable signal or the sensitivity is measured against the ambient noise or the noise of the environment that in fact provides a minimum floor for the sensitivity. However, like any other random quantity, noise is a random process, and due to the fact that it's a random process, then it is best characterized by its average power or average value. In general, a random process, if you look at the random process, the instantaneous value of the random process, let it be an instantaneous voltage or current, doesn't convey much of the useful information. What is very important is average power or variance of this random process, or the average value, or the mean value. Now, in order to have a useful and quantitative measure of the wireless system performance, then we need to calculate the signal power and then compare the signal power against the impairment power, for example, noise power or distortion. And again, since these quantities are best characterized by their powers, then we also calculate the signal power and we evaluate the system performance in terms of how much power it can generate or amplify. Another important notion that one should keep in mind is that at very high frequencies, it is very difficult to measure instantaneous current and voltage, whereas the measurement of the power, for example, using a power detector, power sensor, is rather straightforward at high frequencies. One important consideration here is that when we talk about the power and when we are measuring the power, it's normally the delivery of the power is to a 50 ohm resistance. The reason is that almost all the measurement equipment, for example, in this case that I'm showing the spectrum analyzer, the output port that is coming out of the measurement equipment is 50 ohm. And this is a standard that is adopted by all the instrumentation companies. Again, by looking at spectrum the figure of this picture of the spectrum analyzer manufactured by Keysight Technologies, you see that the signal that is coming in to this spectrum analyzer is in fact has an output resistance of 50 ohm, and that's the reason that we design. Normally, when it comes to the design of the circuits, we design the circuits to load a 50 ohm, particularly if we want to measure them using an external equipment. Now that we understood why power is an important quantity in RF and microwave design, the very next question is, under what condition a power generated by a voltage or current source is maximally delivered to the load? This maximum power delivery from source to the load, in fact, is of central importance in RF design. In response to this question, we can prove a theorem called maximum power transfer theorem that directly answers the question. In other words, given a fixed source impedance ZS, shown here, under what condition for the load, a maximum power generated originally by Vs, in this case, is going to be delivered to the load. It is readily proven that if certain relationship is held between the load impedance and the source impedance, then the power delivered by Vs is maximally delivered to the load. And this condition is called conjugate matching condition. More precisely, if ZL is equal to ZS conjugate, if the imaginary part of ZL is equal to minus the imaginary part of ZS and the real parts are equal, then we have a maximum power delivery to the load. And under this conjugate matching condition, the efficiency of this power delivery is 50%. 50% of the power generated by the source is going to be delivered to the load. So the maximum power transfer theorem is powerful, and it shows that if the load impedance has a certain value relative to the source impedance, then it acquires maximum power from the source. But what if the load impedance is not a complex conjugate matched of the source, which is the case in practice? In other words, there is no guarantee that the load impedance is necessarily equal to conjugate value of the source impedance. Let's consider an example. Let's assume that we have a source with a source impedance of Rs, and this source voltage with its source impedance is connected to an amplifier. This amplifier in general may not have an input resistance or input impedance of 50 ohm. In fact, it could be something like perhaps if it's 50 ohm, let's assume that it's like 30 ohm plus J or minus J, 10 ohm, right? Let's assume that's the case. Then, this conjugate matching principle is violated. Under this condition, can we still guarantee the maximum power transfer from the source to the input of from the source to the input terminal of this amplifier? The answer is yes. And in fact, there is a powerful, very powerful technique that facilitates this maximum power delivery despite the fact that these impedances are not the same. Let's start with an input source Vs, and let's assume that this input source has an input impedance Zs. Okay? And rather than directly connecting this source voltage, let's connect it to a lossless network, a lossless reciprocal network comprising inductor, capacitor, or transformer. Okay? So, assuming that this network is lossless, then we can, in fact, using this matching network, create a condition where when Zs is connected to this so-called matching circuit, from the input of the matching circuit, Ls and Cs and transformers are set such that the input to this matching circuit, Z1, for example, is equal to Zs conjugate. So when it comes to the input power delivered to the network is designed in a way that its input impedance is equal to the conjugate match or the complex conjugate of the source impedance. And likewise, at the output of these two ports, we can design, again, this matching network such that when we are looking at, standing here and looking at the output of this, output port of this matching network, the output port, Z out or Z2, is equal to Z in conjugate, where Z in is the input impedance of this amplifier. With the matching circuit interposed between the source and the load, then we can guarantee a maximum power transfer. And that's the reason that the use of the matching circuit in microwave and RF circuit is essential. Okay, since power is the quantity, then there should be a figure of merit or performance parameter measuring the power amplification of an amplifier or a power amplifier. And there are a number of performance parameters that have been developed or defined. Among those, we can point out to three important definitions of the power gain. For example, we can have the operating power gain GP, which defines the power delivered to the load over power supply to the amplifier, to the input port of the amplifier. Also, there is a definition, another definition for power gain, which is called transducer power gain. And the transducer power gain measures the power delivered to the load over the power available from the source. Another definition for power gain is available power gain, GA, which measures the power available from the network divided by the power available from the source. And among these three definitions of the power gain, the available power gain is the one that is normally used in RF design. And we can see that under the complex conjugate matching or conjugate matching at the input and output, then this available power gain becomes the voltage gain of this amplifier squared. Under the conjugate matching, both at the input and output.